Hello, I'm Florian, and in this short video we're gonna have a look about how you choose the correct injection transformer for your application. There are several important parameters that you need to look at when you choose an injection transformer. One of them is isolation. The injection transformer is isolating you and your analyzer from the system under test. If you have a high voltage system, you want to be sure that your injection transformer is maintaining safe isolation between you and your device under test. The next parameter is of course the bandwidth. If you have a low frequency application, you can choose a lower frequency bandwidth. If you have a high frequency application, you need an injection transformer that can keep up with that high frequencies. The next thing is gain flatness. You want to be sure that your injection transformer has a flat gain over frequency. That's the only way you can ensure that disturbances or any glitches are not coming from your injection transformer, but really from your system under test. Then primary to secondary capacitance. If you have very sensitive circuits or operational amplifier or signal conditioning chains, and if you are injecting there, then you want to be sure to have very low capacitance between primary and secondary, because this capacitance is a parasitic capacitance that you introduce into your circuit. And the last but not least point, saturation. Especially at very low frequencies, saturation is a critical parameter in magnetics. And if you choose your injection transformer, check the datasheets of your manufacturers of choice, and you will find all these values in the datasheet of the product. And next step, we're going to have a look at different products, and we're going to check all these values or some of these values in a real life measurement. Okay, so now let's have a look at these parameters in real life. The first thing, isolation, and that's about safety. So if we look at our products, here you always find a marking that specifies the isolation, and here it says 600 volts category 2 on the B-WIT 100 as well, 600 volts category 2 between primary and secondary isolation. And this means that even if a transient from the line comes in, this isolation will not break. The next thing that we have on our list is bandwidth and gain flatness, and that's somehow related. So I have performed measurements, gain measurements on all the three products I have here, on our B-WIT 100 injection transformer, on our B-LFT 100 low frequency injection transformer, and on a product that I call product R. So let's have a look at our screen, and on the screen I have all the three curves between 1 Hz and 10 MHz. And here we see the red curve, that's our B-WIT 100 injection transformer. It has a beautiful flat gain between roughly 10 Hz and a megahertz, and it goes up to 10 MHz. And it's perfectly flat in that region, and it has nearly no insertion loss, and that's what I call the gain flatness. Then our low frequency injection transformer, this has nearly no attenuation at 1 Hz, so it's perfectly flat from 1 Hz to 10 kHz, and then it starts to roll off. And then we have product R here, that has a quite flat frequency response between 1 Hz and 1 kHz, and then it starts to wiggle around a little bit at high frequency. The gain is not that flat anymore. We have a delta between 2, 3, 4 kHz and 100 kHz of nearly 10 dB, and that's the gain flatness. So from this curve you can already see that the B-WIT 100 injection transformer won't perform very well below 10 Hz if you need a lot of power, because it already introduces quite some attenuation that is also caused by saturation effects. But we will have a look about that a little bit later. So the next point in our list, that's primary to secondary capacitance. And I'm going to measure now the primary to secondary capacitance of our B-WIT 100 injection transformer using a simple multimeter. And if I connect the multimeter between primary and secondary, the reading says 159 picofarads. So the datasheet says typically 160 picofarads. And the next thing, we're going to have a look at the capacitance of product R. That's 525 picofarads, so roughly 4 times higher. The last point, last but not least, that's saturation. And as I already said before, the B-WIT 100 is quite small and tiny. It performs very well at high frequencies, but at 1 Hz you won't drive a lot of power with the B-WIT 100. For that you need a bigger injector and a heavier injector. That's a really big and heavy one, our low frequency injection transformer. And I have now connected the low frequency injection transformer and product R to a signal generator, and I'm creating 1 Hertz sine wave and switch on the output. And now on the scope we can already see that we have 2 signals. We have a blue and a yellow curve. The yellow curve, that's from product R, the blue curve from our B-LFT injection transformer. And then here we have the reading of the peak-to-peak voltage. So let's increase the voltage. We are at 1 Hertz, and now we increase power, increase voltage until we see that some distortion is saturating the transformers. And now we see there are some distortions start to appear, so let's lower until no distortion is there. With clean sine wave, and the B-LFT injection transformer is now injecting into the secondary side 6.4 volts peak to peak, and product R is injecting 3.7 volts peak to peak. So it's roughly 30% more that the B-LFT is injecting right now. Yeah, that was the most important things from my point of view. If you think that I forgot something, feel free to post under the video or send us an email.